but be very, very quiet, okay? You don't want to miss this. You do not have to do this, okay? That gives me 1 plus 3i plus 3i is 6i. I'm going to try not to make a mistake. You wouldn't want to go this fast if you were really doing it. That would be 9i squared. So this gives me negative 8 plus 6i times 1 plus 3i. So I get negative 8 minus 24i plus 6i minus 18, because that would be plus 18i squared. So provided I did this right, adding like terms, I get negative 26 minus 18i. And so I think I'm probably not going to answer your questions, Zaina, because I've now taken a point and cubed it. Now I'm just talking about numbers. Like, there's no reason for me, well, I say there's no reason for me to graph it. You'll see an interesting graph in a few minutes though with that.
I was
But
just wondering what the correlation is between I and I to the 5th and I to the 9th and stuff like that, and how it goes
Like-
around. And it's 1, 2, 3, 4, 1, like, you know what I mean?
It's again like I planted you in the audience. I'll show you. So I think I am going to answer that question now that I think about it. But just hang on. All right, now I did all that FOIL. Okay, girls, watch. Did all that FOIL. I could write it as a trigonometric form of a complex number, though. All right. And so 1 plus 3i. If I did the square root of 1 squared plus 3 squared, I would have square root of 10. And then cosine I sine. Oh, darn. I didn't really want to do this one. I meant to have square root of 3 so we would know the angle. But I've gone this far. So a few calculators out in radians. Now we're going off-road, hoping that this works out really wonderfully for your teacher. All right? So I'm going to say tangent of theta is 3 over 1. I'm in the first quadrant. Can y'all see this, that I have 1 plus 3i in the first quadrant? So I'm okay with the angle that you report to me. What is theta? 1.249? Okay, and some of you keep that long number in your calculator. 1.249, which makes sense to me because this is about 1.571 pi over 2 if you divide pi by 2. All right, now if I want to raise this to the third power, there's a trick to doing it like there was a trick to adding and multiplying. The trick is based on what we've already seen, okay? Probably not going to prove it to you, but if I did the complex times the complex times the complex, the trig form of a complex number, the trig form times the trig form times the trig form, we'd see that when I multiply, I add and all of that stuff. So it all still comes into play with what we just did. That may or may not help you, okay? But what I'm going to do is I'm going to say, darn, I wish I'd used square root of 3 because I can't even look in the book. Okay, so anyway, what you're going to do is you're going to raise the radius to the power. So I have square root of 10 to the third. And then you multiply the power by 3. So if I multiply the power by 3, I need you girls to say times 3.
3.747.
Hopefully you just said times answer or something.
Yeah.
Okay. So Lily's got like a longer thing in her calculator. Now before this looks really weird, it shouldn't. Because you know when you're multiplying 2 of them, you multiply square root of 10 times square root of 10, and you would add the angles. Do you remember your homework? So if you have 3 of them, you see that would happen 3 times. You'd have square root of 10 times square root of 10 times square root of 10. And then you would have 3 angles to add together if I stretched it out like last night's homework, if you want to know why. But look how easy that is, okay? Now, hopefully, oh, and by the way, you might see it written like this, 10 to the 3 halves times cosine of 3.747 plus I sine of 3.747. All right, do y'all remember the square root of 10 is the same thing as 10 to the 1/2 power? And then if I cube it, It just looked kind of funny to me to have the square root of 10 cubed. I'd rather just use an exponent for the whole entire thing. Now let's hope this works. I'm going to get Elena and Lily, or anybody else following along on the calculator. If you would say 10 to the 3/2 power times the cosine of maybe your answer, 3.747.
So the full answer?
The 3 point, yeah. She got negative 26. It's got a whole lot of zeros and then a 2 at the very end of about 9 or 10 zeros just because of our rounding issues. But do you see that this also worked? Guess what's going to happen if I get Lily to say 10 to the 3/2 times sine of 3.747? She's going to get negative 18. All right, so my point is I folded it out and I erased it. And then I did it with the trig form. Let me show you why you're learning trig form. Because the one actually in the book did not say to the 3rd power. You'll see these for homework because you should be sitting there going, I'll just FOIL it out. I don't want to do that, okay? But no, you don't. So the one in the book actually said 1 plus root 3 to the 12th power. You do not, I had an I. You do not want to go 1 plus root 3i times itself 12 times, I promise, and think that you're going to pull it off, even if you're good at the binomial theorem, which you're probably not. But anyway, not your fault. Most people in pre-cal are just like, don't remember Pascal's triangle binomial theorem, but you did it. I'm good at binomial theorem. You may be great at it. I don't want to do it, okay? So I'm really excited about the trig form of a complex number. All right, so my modulus is going to end up being the square root of 1 plus the square root of 3 squared. It's going to end up being cute little 2 in this new problem. And then I have cosine plus I sine. I'm going to have tangent of an angle is root 3 over 1. So what angle do we have? Pi over 3. I know I'm in the first quadrant because of the positives. So I have pi over 3. Pi over 3. Now, to raise all of this to the 12th power, I can use my trick. I can say 2 to the 12th, because when I was multiplying, remember you multiply all your things in the front, and then you were adding all of your angles. That's why I'm going to say 12 times pi over 3. So I'll get 12 pi over 3. I sine of 12 pi over 3. Isn't that beautiful? It's a whole lot better than all that FOIL. And now if you want the answer back in rectangular form, do you see you just multiply those? All right, so what you do is you have your radius times cosine theta plus I sine theta to a power. You say r to that power, and then you say cosine of n theta plus I sine of n theta. You may have to think about why this works based on the multiplication you learned.
How come it's pi over 4?
Because it's
12 pi over 3. Oh, I'm so sorry. That's why y'all were looking confused. That should be what? So sorry. That's why I wrote all of this down, because I saw confusion on the back row, but that's my fault. I thought you just don't understand. Let me explain it to you. Okay. So that would be 4 pi. Thank you, Zana and Pietra. I can trust your faces. Okay. There's also something that Atir did something. She just stood here next to it and it started working. Okay.
yeah.
There's also a way you could take a root. So I'm going to keep teaching for about 5 more minutes while you leave. But remember to look at the end of the video for the rest of your homework, okay? Bye. Without teaching no one. Thanks, girls. Oh, Zaina. At the end of the video, I'll actually graph what's happening.
Okay.
And it's really cool what happens. And we'll talk about it first or next class. Thanks. Okay, So if we're going to take the cube root of negative 2 plus 2i, and so in order to take the roots of a complex number, you're going to do the same thing that we just talked about. You have negative 2 plus 2i to the 1/3 power. So you're going to raise your radius to the 1/3 power. But then we're going to have to do something else with our angles. So let me write it down. We're going to say r to the 1/n, or the nth root. And then we're going to say cosine. I'll explain this. But you're going to have theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n. Because there could be, we should end up with 3 of these, where k goes from 0 to 1 to 2. We can talk about y more in the next class. But first I've got to write this in trigonometric form. And so if I go negative 2, if I find the square root of that, I get square root of 8, which I'm going to leave. And then I have cosine. If I take the tangent of theta and put 2 over negative 2, I get tangent theta equals negative 1. If we go back to up 2, we're in the second quadrant. So that would be 3 pi over 4. All right, and the book actually did this one in degrees, so I'm just going to go ahead and do it in radians. Or do I want to do it in degrees? I'm going to do this in degrees so you can look at the example in the book. So in degrees, this would be a 360, and theta would be 135. So I would take my angle 135 plus 360 times my first number, 0, divided by n, which is 3, because you're taking the nth root, plus I sine of 135 plus 360 times 0 over 3. So it's like I'm raising it to a power. So you can learn this and do the same thing if it's 1/3. However, if you're taking a cube root, just like there could be more than one answer in terms of imaginary numbers. Like for instance, if you have the square root of 4 in real numbers, the answer is just 2. But in imaginary numbers, it would also, an answer would be 2i, because 2i times 2i is 4i. Sorry, it's wrong. There's only one of those. It's like if you have the square root of negative 4, you would have 2i. So I'll explain it as we find them. So this is the square root of 8. This is the cosine of 135 plus 0 divided by 3 is 45. I sine of 45 is my first answer. Oh, I'm sorry. I was supposed to say r, which is the square root of 8. So I'm taking the cube root of the square root of 8, which looks really ugly, as would the cube root of 2 root 2 look really ugly. So that's why I was talking earlier in class we use exponents. 8 to the 1/2 to the 1/3 power. So I'm going to write this as 8 to the 1/6 out here. So I take the cube root of the cube root of r. I'm sorry, the cube root of the square root. So I take the cube root of whatever I get for r, which was square root of 8. I'm going to write it as 8 to the 1/6 out here. All right, which I can actually reduce to this. 8 is 2 to the 3rd to the 1/6 power. So all of that ends up being just 2 to the 1/2, which is root 2 out here. All right, now I have a second answer. So I have root 2 times the cosine, and now I go around 360 degrees another time. If it's to the 1/3 power, you go out 1, 2, 3, starting at 0 and then go 2 more. So what you're doing is you're finding your answer, rotating around, and rotating around. And I'll show you what happens in the end. All right, so if I go around 360 degrees plus 135 is 495. And 495 divided by 3 is 165 plus I sine of 165. And my third option is the square root of 2 times. Now you can really move a little faster because you can divide this up into 135 divided by 3 is 45. And 360 divided by 3, you keep adding 120. So the next one would be if I added 120 to 165, I'd get 285 plus I sine of 285. Now if you add 120 again, you go past 360. So these three answers actually happen before you get all the way around your circle. If you actually graph these, where you turn 45 degrees and you go out square root of 2, and then you turn 165 degrees and go out square root of 2, and then you do 285 degrees and go out square root of 2. You see how they're placed around your circle? An answer here, an answer here, and an answer here would all be the cube roots of this number right here. Oh, it doesn't matter. I just need to do a couple more examples. You can talk. There's usually lots going on. All right, so you can also use it for something like this. X to the 6 minus 1 equals 0. The fundamental theorem of algebra tells us that there are definitely 6 roots. It's just that some of them will be real and some of them will be imaginary. So there's definitely 6 complex roots. If you're doing a cube root, we should get 3 roots. Alright, so I'm going to say x to the 6 equals 1. And I'm going to take the 6th root of 1. So we know one of our answers is going to be 1. Another answer is going to be negative 1, but we're going to find them all. There's 4 more. Alright, so I'm going to write 1 in complex numbers, so I have 1 plus 0i, which is going to be, my modulus is going to be the square root of 1 squared plus 0 squared. So it's going to be 1 cosine, if you go out 1 and up 0, then you're using 0 degrees or 0 radians. We use radians this time, plus I sine 0, or whatever your angle happened to be. And now I'm going to take the 6th root of that, which means I take the 6th root of 1 times cosine of 0 plus 2 pi k over 6 plus I sine 2 pi k over 6. You need 6 of them, so you have 0, 1, 2, 3, 4, and 5. Because there should be 6 of them that work. So the 6th root of 1 is obviously 1. When I use 0 for k, I just get the cosine of 0 plus I sine 0. The next one, when I put in 1 for k, I get 1 times the cosine. When I put in 1 for k, I get 0 plus 2 pi times 1 over 6. So I get 0 plus 2 pi over 6, which is pi over 3. If you want to move a little faster, we realize that we keep adding by pi over 3's. So this 1's cosine. So we're taking, it's like you're adding the period to it when we were solving trig equations. So we're adding by every pi over 3k that it repeats itself. So if we have pi over 3 and pi over 3, this next one's 2 pi over 3. And then if we add pi over 3, we get 4 pi over 3. Another pi over 3. We get 5 pi over 3. Let's see, 0, 1, 2. Oh, I skipped 3. Sorry, I knew I skipped 1. So on the third one, you would have 1 times the cosine 2 pi over 3, and pi over 3 is 3 pi over 3, I sine of pi. This is the fourth one, and this is the fifth root. So we have 6 roots. If we check them, this one is just going to be the cosine of 0 is 1, the sine of 0 is 0. This one gives me 1. If I do this one, it's going to be 1 times the cosine of pi over 3 plus I sine of pi over 3, which is going to be root 3 over 2i. And then I would get this one, whatever that is. This one would be cosine of pi is negative 1. So that would give me my 2 reals. And these are going to give me my 4 imaginaries right here. If you took time to actually multiply them out to the 6th power, you would get 1, so we can solve algebraic equations that way. If I graph them like Zana was asking, I would start out here at 1. Every pi over 3 radians, I would have another one. And so this one, if I go out 1/2 and up square root of 3 over 2, I have another one. And then if you figured out what this one would be, it'd be in the second quadrant. The 4 pi over 3 one. Oh, I'm sorry, I keep forgetting about this one. This one would land right here. The 4 pi over 3 would be right here. Be more down this way. And then the 5 pi over 3 would be like this. And so they go around your circle in an even manner, like that. So if you want to solve something like this, you would write it as 8 plus 0i. You would find your argument, which would be the square root of 8 squared, so that would be 8 times cosine. You would find your angle, which in this case again would be 0, plus I sine 0. And then you would take the 4th root of it to solve for x, and there should be 4 answers. So I would take 8 to the 1/4, and then I would say cosine of theta plus 0 plus, and then I would say 2 pi k, and I would divide it by 4, plus I sine of 0 plus 2 pi k, and divide it by 4. You won't always have an angle of 0 like we have in my first 2 examples, but you can look back to my second 2 examples. Let's look at 8 to the 1/4. This is 8 is 2 to the 3rd to the 1/4 power, and so you could actually call this 2 to the 3/4 would be the same thing. Then you would have cosine. First of all, if you're doing a 4th root, you're going to fill in 0, 1, 2, and 3. If we fill in 0, we're just going to get 0. And you can see if you if you work this out, you would get 2 to the 3/4. And if you raise that to the 4th power, you would definitely get 8. So that's an easy one. Then what I would do is keep my r, 2 to the 3/4. And then I'm going to add 1. So if I put in 1, I get 2 pi over 4, which is pi over 2. So I have cosine of pi over 2 plus I sine of pi over 2. Let's say that would give me sine of pi over 2. That would give me 2 to the 3/4 I. Then you'd have 2 to the 3/4, and you would add another pi over 2 when you put in 2. And so you would get cosine of pi. And then your 4th one, you put in 3. You would get 6 pi over 2, which of course is 3 pi over 2. You can find all sorts of ways to move a little faster because it's your unit circle divided into 4 equal parts or 6 equal parts or whatever. And if you graphed them, they would move around your circle every 90 degrees, every pi over 2.